In this lesson, we'll learn 6 connection rules for simplifying block diagrams. These rules let us reduce complex systems with multiple blocks and feedback loops into simpler equivalent forms. We'll then apply them step by step to simplify the DC motor block diagram from Lesson 9. The first 2 rules are straightforward. In a parallel connection, 2 blocks G1 and G2 share the same input and their outputs are summed. The equivalent is a single block, G1 plus G2. In a series connection, the output of G1 feeds directly into G2. The equivalent single block is G1 times G2. Next, 3 summation rules. Summation 1. If a block G receives the sum of 2 inputs U1 and U2, we can split it into 2 parallel paths, each through G. Summation 2. If a signal U2 is added after block G, we can move the addition before G by passing U2 through 1 over G. Summation 3. Summation points can be freely rearranged. The order of addition doesn't matter. The most important rule is the feedback rule. A forward path G1 has a feedback path G2 returning from output to input. For negative feedback, the input to G1 is U minus G2 times Y. So Y equals G1 times the quantity U minus G2Y. Rearranging Y times 1 plus G1G2 equals G1U. The closed loop transfer function is G1 divided by 1 plus G1G2. For positive feedback, the denominator becomes 1 minus G1G2. Now let's apply these rules to the DC motor from Lesson 9. The full block diagram has input voltage U through a summation, then 1 over LAS for inductance producing armature current. Current times C phi F gives electrical torque. After subtracting load torque TL, the integrator 1 over Js gives angular velocity omega. The Ra feedback models armature resistance and C phi F feedback models back EMF. Step 1. Simplify the inner Ra feedback loop. The forward path has gain 1 over La S and the feedback gain is Ra. Applying the feedback rule, the closed loop becomes 1 over La S plus Ra. Combining this in series with C phi F, we get G1 equals C phi F divided by La S plus Ra. This represents the simplified path from voltage to electrical torque. Step 2. Simplify the outer feedback loop. We rearrange using the summation rule so that the TL disturbance enters after the feedback is resolved. The forward path is 1 over Js and the loop gain involves C phi F squared over LAS plus Ra. Applying the feedback rule gives G2 equals 1 over Js divided by 1 plus C phi F squared over Js times LAS plus Ra. The final simplified system is elegant. Voltage U passes through G1, load torque TL is subtracted, and G2 produces angular velocity omega. This gives us 2 clean transfer functions. Input-output, omega over U equals G1 times G2. Disturbance-output, omega over TL equals negative G2. Using typical DC motor parameters, the step response shows omega rising to about 20 radians per second. The disturbance response shows a drop of about 4 radians per second from a small torque load. Both settle within about 50 milliseconds. To summarize, 6 connection rules form our simplification toolkit parallel, series, 3 summation rules, and the crucial feedback rule, G1 over 1 plus G1G2. We reduced the DC motor from a complex 5-block diagram to a clean 2-block cascade. This separation of input-output and disturbance-output behavior is fundamental to control system design.